Hello, Tensor friends. I have done this Dell operator in bits and pieces in various videos I've done, and what I did now is I put it all together, and I want to show how you can derive the Dell operator in spherical the coordinates using Tensor the calculus. Because traditionally this is done with vector the calculus, and I'll show you just a bit of that at the end, and why this is so much easier. Remember the difference. Tensor calculus is the generalized format of vector calculus, okay? So you have the Dell operator in Cartesian, the coordinates. It's given as this upside down triangle. And it represents the partial derivative of the coordinates times the basis of the vectors, okay? So this is an operator, so it has to act on something. And if you use the Dell operator to act on a scalar of the field, you get a vector of the field, and we call that the gradient. So it'd be the gradient of f. If we use that operator to act on a vector of the field via the product, we call that a scalar the field, and it's the divergence of v. Okay, so del dot v is a scalar field, and we call it the divergence of v. Now, there's one more. If the del operates on a vector field via the cross product, that yields a vector field, and we call that the curl of v. So here's three very common ways you see in science and engineering the del operator is used, okay? So how can we express the del operator as a tensor equation, okay? Here's a couple ways. So we're saying the del operator of the scalar field, I chose this because it's easy, would be the covariant derivative of f times the contravariant basis vector. We also could express it as the contravariant derivative of that scalar field times a covariant basis vector. Now, traditionally, we would want this in our work and this in our work. Well, how do we get all this together? Okay. Well, we could do that with our old friend, the metric tensor. It's used to raise, it can be used to raise or lower indices, okay? So if I multiply the covariant derivative of the j with respect to this inverse metric tensor, gij, the j's are contracted out and we're just left with I. So I can put this right back in here and I get this expression, okay? Now, just a real quick review. What is the covariant derivative? Okay, the covariant derivative as an example of a one-index tensor like this. So the first thing you would do is write down the normal partial derivative of that. This is a contravariant vector component with respect to this arbitrary, the coordinate I, see? And then you add a term, because it's contravariant, you do a positive. You add a term that may account for the changes in basis vectors. All right. So just a one index tensor gives this expression. All right. Well, let's look at what we got. Well, we've got a covariant derivative of a scalar, the field. All right. So you write down your normal, the partial derivative with respect to the coordinate I, and you add what? What do you add? Well, this is a tensor rank 0. It has no indices, so I can't add anything. So the covariant derivative of a scalar field or scalar is the same as a partial derivative. So now that we know that, we can just put this in for all of this stuff, and we get this very simple expression. So the del operator of this scalar field is equal to the inverse metric tensor times the partial derivative of that field times a covariant basis vector. So, and this is a generalized equation of the gradient that works in any coordinate of the system. Excuse me. And the good thing about using the gradient is I can just yank it out and I've got just the del operator. Okay. So we want to use that in spherical the coordinates. Okay. And here's the drawing we have of how to come up with these four equations. The details of this, I did this in gory detail, and I'll leave a link to that video in the description. of how we found this radius, the projections, all these projections, and how we come up with these equations. I won't include it here because it's lengthy, but I'll leave a link. Okay, so we've got these 4 transpose equations. Now we want to use those to find our basis vectors in spherical coordinates, which would be ER, E theta, and E phi. Okay, so we're going to let R, theta, and phi be the unprimed coordinate system, and XYZ be the prime coordinate system. So we're going to do this the right way. We're going to use the Jacobian, because last time I didn't, I got in trouble. Okay, so here's our generalized equation. So the unprimed basis vector is equal to the Jacobian times the prime basis vector. And all you have to remember is you got one free index, and it has to be in the same position here and here, and everything else is primed. And what does that mean? That is the partial derivative of the coordinate in the prime system divided the derivative of the unprimed, the system. Okay, so let's write out what it actually is. So let I equal R. So the free index is R. We know we have 3 dimensions, so we're going to have 3 terms. So in each term, there has to be an R on the bottom, right? R, R, R. Then this is a summation index. So it's going, first case is X, second case is Y, third case is Z. Okay? Here's our transform equations. So we can do all this in our head. So what is the partial of X with respect to R? Well, these are constants, and a derivative of R is 1. So we just get these 2 constants. What is Y with respect to R? The same thing. We get these 2 constants, derivative, that's 1. The same thing, cosine theta, 1. Okay? Now, let's do theta. All right? So the free index now is theta. It's got theta, 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 X, Y, and Z. Same format every time. All right? Now, here's our 3 transform equations. Now, this time, we're taking it with respect to theta. So R and phi are constants. Derivative of sine is cosine. R and phi are constants. Derivative of sine is cosine. R is a constant. Derivative of cosine is minus sine. Okay? Everybody follow? All right, the last one is phi, the same format. Phi, 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 X, Y, Z. Okay, let's do this. And R and theta are constants. Derivative of cosine is minus sine. R and theta are constants. Derivative of sine is cosine. There is no phi in here, so it's 0. All right, so now we have our 3 basis vectors. So now we can use those to find our metric tensor in spherical coordinates, which looks like this. All right, so it's the dot product of all the permutations of the basis vectors, and usually they're collected in a nice little matrix like this. And all of these off terms here, this one, this one, this one, the mixed terms rather, this one, this one, this one, are all 0. And why is that? Let's go look at it. Okay, so we have a sphere in 3 dimensions. We have a point on the sphere. And at that point, we can define those basis vectors we just come up with, which was ER, E theta, and E phi. And you can see they are all at right angles to each other. So they are orthogonal. And you know what that means. The cosine of the angle between them is 90. The cosine of 90 is 0. So all the mixed terms are 0. Okay, so all we're going to have is a GRR, G theta theta, G phi phi. We multiply these out, right? So ER dot ER is the same as ER squared. And once again, we're going to square a polynomial with 3 terms. We should get 9, but we don't, because EX dot EX is 1, EY dot EY is 1, EZ dot EZ is 1, but EX dot EY is 0. And EY dot EZ is 0, etc. So we only get 3 terms. So it's real easy to square it. Excuse me. So we do that. We do some algebra, bada bing. We come down with these trig identity. So ER is 1. We do the same thing with E theta. We go through, we simplify, 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 and we come out with R squared. E phi, the same thing, square everything, and we get R squared sine squared theta. Okay? Now, what we just did was the covariant metric tensor. We need the contravariant metric tensor or the inverse metric tensor, which is easy to do because all of these off diagonals are 0, so we don't have to do anything sexy. We just put all this under 1, and we got the inverse metric tensor, right? That's just that easy. Now we can use our equation, which was this. I just took out the f because we're just making an operator, okay? So we put all that in. So GRR is 1, and we're taking the partial with respect to I, which is R, and J, which is R. And then G theta is 1 over R squared, partial with respect to theta, E theta, plus G phi, which is this, 1 over R squared, sine squared theta, the partial with respect to theta, E phi. Partial with respect to phi, E phi. All right, so this is the Dale operator in spherical, the coordinates, but you say, well, that's not how I remember it. You're right. Most textbooks, they want the Dale operator with unit basis vectors. I don't know why, but they do. Okay, so how do you find a unit basis vector? Well, you divide the basis vector by its magnitude. All right, so that's easy. We go through and do that. It turns out that R hat is the same. It's the same as ER. It's 1. And phi hat's equal to R, and theta hat's equal to R, and phi hat's equal to R sine theta. So we put that back in, and this is probably the equation you see in your textbooks, okay? So that's how easy it is to do a tensor calculus. Now, how do you do it with in vector calculus? All right, so you start with the thing, the operator. Now you've got to do the multivariable chain rule like this, where you have to solve all of these differentials, and then you have to do a bunch of algebra to put it all together. So you're solving a system of linear equations once you're done. It's not hard to do. It's just extremely lengthy, and there's lots of rooms for mistakes because you're taking derivative of some funky things like this, which is, that's not easy. It's not for me anyway. All right, so that's it. See you later.